Scholars, our job as we step for the first time really into calculus is to talk about the difference between average speed and instantaneous speed. And we're going to see how it connects together with some of the things we've been talking about, infinitesimals and finding slope. So probably some of you are already driving, you have this idea in your head that if you drove 200 miles and it took you 4 hours, you could compute your average speed. 200 miles divided by 4 hours makes 50 miles an hour. The 200 divided by 4 is the 50, and we have this new units, miles divided by hours, miles per hour. So in general, speed can be computed by finding the change in distance and dividing it by the change in time. So you see a place on your paper for you to write that in. You can write it in with words, you can write it in with the symbols. Notice here I've used delta x to stand for change in distance and delta t to stand for change in time. You'll notice that we will use lots of different variables in calculus, so I don't want you to get too attached to using those specific letters. But in general, change in distance divided by change in time to find average speed. Now, we talked about this a little bit, and what's new in calculus is we're going to be able to think about our average speed, but we still also notice that it's very unlikely that we were actually driving 50 miles per hour for that whole 4 hours. So at any particular point along the trip, you might have looked down at your speedometer, or maybe a police officer had a radar gun trained on you and zap, found out that at a particular moment you were going 65 miles per hour. Or there could have been a time when you were going 3 miles an hour or 100 miles an hour. Those speeds at those exact moments in time, those are called instantaneous speeds. So speed at an exact moment. We want to make sure we talk about the difference between those. So before we talk too much more about instantaneous speed, let's do an example of how to compute average speed. So you have a function there. If there's a rock that's going to fall, and we have a formula that can tell us the distance that that rock is going to fall after a certain amount of time. That 16 that you see in that formula comes from the force of gravity pulling the rock down toward the earth. So I've called that function f of t. I've also called it y, just sort of to imply that it's a change in height as opposed to a horizontal change that I might have called x. So a change in height. And we know the position of the rock is given by this function, 16 times t squared. So I could have written in here, let me write it in right now. After 0 seconds, how far has the rock fallen? After 0 seconds, it's going to be 16 times 0 squared, which 0 feet. So after 0 seconds, the rock has fallen 0 feet. 2 seconds after it started falling, I'm going to evaluate this expression, 16 times t squared, for t equals 2. And I get that the rock is at position 64 feet below where it started after 2 seconds. So to be very specific, change in distance, so distance is change in position. So I'm going to subtract those two values. That's 0. I'm going to take away from 64. So 64 minus 0 divided by change in time. So the second time minus the first time. And that's where I get this expression, 64 feet divided by 2 seconds, which you can simplify to 32 feet per second. So over those 2 seconds that it falls, the average speed of the rock is 32 feet per second. So maybe you already have an idea from your physics class or from your algebra class what this is going to look like if I have something that's falling with a position function of 16t squared. It's going to fall very slowly at first, and then gravity starts pulling it toward the earth faster and faster and faster, so the rock is going to fall faster and faster and faster. So it's not the case that there is one speed for this rock. If you looked at the rock's speedometer, it would be changing, and the speed would increase and increase and increase until it crash landed somewhere. So we want to talk about this new idea now. How could we find the instantaneous speed of the rock at exactly the time 2 seconds after it started falling? If you had a police officer's radar gun trained on the rock at exactly 2 seconds after it falls, how fast is the rock going? So before I move the slide, just remember, this is what we just computed to find the average speed of the rock. We found the position at time 2, subtracted the position at time 0, and divided that result by the difference between time 2 and time 0. So change in position divided by change in time. So if I want to use that same kind of math, and it turns out I can use that same kind of math to find out instantaneous speed, my only problem is that I've found this speed over the average speed over a long time interval, 2 whole seconds. And really what I want to find is the change in distance divided by a very, very, very small change in time. Instead of 2 whole seconds, I want to find the change in distance divided by change over like 0.0001 second or 0.000000 second. Remember we talked in class about infinitesimals. That's what's going to separate the math of calculus from all the other math you've done, is we're going to need a way to talk about using numbers so small that they're practically 0. Because if I really had a change in time in my denominator that was 0, all of a sudden I would have a divide by 0 problem and wouldn't be able to simplify that expression. So it turns out that's a big problem that mathematicians, physicists were trying to get over, was dividing by 0, and that's what led to the development of calculus. So watch what I'm going to do. Instead of using time 2 and time 0, remember I had f of 2 minus f of 0 over 2 minus 0, I'm going to use f of 2 and f of a teeny tiny bit more than 2. And instead of having to say teeny tiny over and over again, I'm going to use a variable. I'm going to call it h. And I'm going to let it stand for a very, 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 very small change in time. So my new expression for instantaneous velocity, you can see up here. I'm going to find f of 2 plus a tiny bit minus f of 2 over 2 plus a tiny bit minus 2. So change in position divided by change in time. It's just now the distance between my 2 times is very, very, very small. So small, I had to give it a name. I'm just going to call it h. So here's what we have, and this is my f function with 2 plus h plugged in for t. This is my f function with 2 plugged in for t. And then 2 plus h minus 2, that simplifies to h in the denominator. So this can help me think about what's going on, but if I actually tried to do this math, see, I want h to be so small, it's practically 0, I'm going to have a divide by 0 problem. So one way to get around this is I can use my calculator or my computer to try to plug in smaller and smaller and smaller values of h so that they get really small, and I can maybe start to see if there's any patterns that I can use to evaluate this expression. So watch what happens. If I let h be 1, then I'm going to use f of 3 and f of 2, and my denominator is going to be 3 take away 2 is 1. I get a instantaneous speed of 80. If I let h get smaller and smaller, I can see what happens to those instantaneous speed values. They get closer and closer and closer to 64. And if you've guessed that if I let h get even smaller, then those outputs will get closer and even closer to 64. So we're just going to start to use this language. We say that the velocity has a limiting value of 64. We've talked about asymptotes, a line that your graph approaches. We also can talk about values that your function approaches. Same kind of idea. And notice here, I could never actually let h be 0 because I would have that divide by 0 problem. But if I go through this process, I can start to imagine what that final result would be if I were to let h actually get to equal 0. And then you can see here, why might we not want to do this? Okay, we're not always going to have a calculator or a computer, and it's tedious to plug those very small values of h in by hand. So what we want to do is take this same idea. On your calculators, you sort of got to this same idea by zooming in and zooming in and zooming in on our natural log function. We're going to talk about an algebra way to simplify this expression so that we can get over that divide by 0 problem, but still just use algebra to simplify this expression. Okay, so I'm going to start off. I'm going to find f of 2 plus h minus f of 2 all over 2 plus h minus 2. So this is a little bit simplified already. you can see that 2 plus h minus 2 has been simplified to h in the denominator. And the question is, can I simplify this algebraically? And the answer is yes. So you're going to have to dig back to how you simplified polynomial expressions. If I took that expression 2 plus h and I wanted to square it, I could multiply 2 plus h times 2 plus h. It takes 4 multiplications, and we get this new expression. So instead of 2 plus h squared, I can rewrite that as 4 plus 4h plus h squared. I can distribute that distribute that 16, simplify this expression. Notice I'll have this here, 16 times 4 makes 64, and at the end, I'm subtracting 64, so those 64s cancel out. I end up with 64h plus 16h squared all over h. So you can see there's just some suggestions here. That's expanding the numerator using algebra and simplifying, canceling out those 64s. Okay, I still have a divide by 0 problem because I really want h to be 0, and I still have a 0 in the denominator. But watch what happens. I can factor that h out of the numerator. I have an h in the numerator. We'll cancel with an h in the denominator. Now I have to get me out of the way so you can see. So watch what happens. My new expression for the instantaneous velocity is here. 64 plus 16 times h. But h is a very, very, very small number, so small it's essentially 0. Now, I don't have a divide by 0 problem anymore. I had division here. In this part, there's no division left. I can simply replace h with 0, and I can simplify the result. I have 64 feet per second. This is still a speed computation, so the same units, feet per second, distance per time. And you can see that that matches what we were expecting the answer to be when we plugged in values for h and let them get smaller and smaller.